place. So some of the states are less than 40, and then some of the states are like above 70. Because, some states people are just suspicious, or, they've gotten mixed messages, which is really unfortunate. So just this afternoon, President Biden said that all U.S. government employees will have to be vaccinated within 75 days unless they have legitimate medical excuse. And they're also requiring vaccinations for people in some critical areas, like some child care facilities, I think, and things like that. And most healthcare providers are required to be vaccinated, most doctors and nurses and other people who work in hospitals, but not everybody. So frustrating.
Yeah, I hope everything will be better. Yeah.
Yeah, me too. Inshallah.
Thank you.
Inshallah. Okay, I think we have enough participants today, Professor Alan.
Okay.
I will give some brief introduction to participant. Maybe new student join this class today.
Okay.
Good morning, everyone. Today we will continue lecturing from Professor Alan. So he will continue what he teach to us yesterday. Now, I hope we will enjoy this lecturing class today, and I hope we got a lot of questions regarding this new knowledge for us. Professor Alan, time and place is yours.
Okay, thank you, Jadvan. Thank you, everyone. Assalamu alaikum again. Happy Friday. And I am going to move into my second set of notes, which I emailed to Jadvan yesterday on groundwater recharge and groundwater surface water interactions. And I promise to allow more time for questions today. I'm sorry I ran a bit long yesterday. But also, if you have any questions in the meantime while I am talking, feel free to put them in the chat. Feel free to ask me. With 32 participants, I don't always see everybody's face, but I can see questions in the chat pretty easily. So thanks, Faisal, for letting me know. I'm going to share my screen, and I will go into slideshow mode here, hopefully. There we go. Okay. So where I began talking yesterday was just about fundamentals of hydrogeology, basically about the physical aspects of groundwater flow and about the parameters that control groundwater flow and the occurrence of groundwater in the subsurface, types of porosity, concepts like permeability and hydraulic conductivity and hydraulic gradient. I talked about pumping tests and land subsidence and types of aquifers and confining units, how water is yielded when an aquifer is pumped, depending upon whether the aquifer is confined or unconfined, or as we say, leaky confined, which means that there is a confining unit above it, but the confining unit leaks water. So I'll build on those concepts in what I'm going to be talking about today. A number of the diagrams that I showed yesterday were from the book by Fitz, Groundwater Science, and I highly recommend that. It's available from Elsevier. Our library actually has a digital copy of it, but it's quite thorough. So this is another diagram from Fitz, again, just showing the kind of components of the subsurface. And I didn't use this term yesterday, but we use the term reservoir. Many of you are probably familiar with a reservoir as being a body of water that is like an artificial lake. created by a dam across a stream. But in this case, we use reservoir in a different sense. A reservoir is literally where water resides, where it is. And so in this case, in large type, the reservoirs are the unsaturated zone and the saturated zone, and a river representing a body of surface water. And then the fluxes that are shown include precipitation, overland flow, and interflow, which are the surface and subsurface components of runoff. Infiltration, some of the water that infiltrates is diverted as interflow before it reaches the water table. Some of it may be lost by transpiration. Note that transpiration and evaporation are combined here into a single water vapor flux term, evapotranspiration. And then some of the water that infiltrates may recharge groundwater. And again, the water table is denoted with this upside down triangle or gradient operator. And under natural conditions, groundwater flows from the recharge zone to the discharge zone, in this case, the river. But when pumping occurs, some of that water is captured and discharges by pumping instead. So we talked about most of these processes yesterday, and I will go into some of them in more detail now. So the next question we can ask is, let me make sure I'm on the slide I want to be. Yeah. When does groundwater recharge occur? And so we can ask that question seasonally. And this is a diagram from Domenico and Schwartz, another hydrogeology textbook. And you see qualitatively shown on the y-axis inches of water, an inch is 2.5 centimeters. It's an English unit we still use in the United States. And so this y-axis denotes fluxes either in terms of evapotranspiration or precipitation, and soil moisture fluxes, either depletion, that is uptake by plants or loss by evaporation, or soil moisture recharge. And so this diagram relates precipitation to potential evapotranspiration. So if you remember about evapotranspiration, it is the combination of evaporation and transpiration as a combined water vapor flux to the atmosphere. Potential evapotranspiration is simply the maximum possible evapotranspiration, and it approximates open water evaporation from a free surface. Well, this shows basically what we expect in mid-latitude regions in North America and perhaps in Europe, where the winter extends from November and December, shown on the right-hand side of the graph, or strictly speaking, December, through January and February and March. So our cold season basically is from the middle of October to the middle of March. And we don't really have distinct wet and dry seasons for most of North America like you have in the tropics. Instead, our summer, or spring, summer, and autumn really is our warm season, beginning in late March, early April, and extending to October. And so where precipitation is in excess of potential evapotranspiration, you have the soil moisture being recharged and potentially groundwater being recharged as well. And where precipitation is less than potential evapotranspiration, you have soil moisture depletion. So during the cool season, when the plants are not actively growing, you don't have as much transpiration and you have lower temperatures, so you also have a lower rate of precipitation. So overall, potential evapotranspiration is going to be less than precipitation, even though the maximum precipitation, as shown here, may occur in the summer. Conversely, in the summer, you have the growing season and you have higher temperatures, so you're going to have more evapotranspiration. As I asked the students in my class here in Kentucky, do you expect this to be true everywhere, this relationship? And so I get them to think, for example, about the Southern Hemisphere, like Australia, where it might be 6 months out of phase. And the winter is basically June, July, August, and September. or in the tropics, where again, you may have a distinct wet season and a distinct dry season. So this relationship in terms of seasonal recharge, in terms of the timing of when recharge occurs, is going to vary depending upon where you are on the planet. But even in temperate regions, you may have recharge during the summertime, and it just depends upon the antecedent moisture conditions, that is how dry the soil is, and the intensity and duration of rainfall. And so this is a graph or a set of graphs from a US Geological Survey report called Basic Groundwater Hydrology by Heath, another of the references that I use in my hydrogeology class. And you can see on the bottom rainfall in millimeters for the year 1978 at a station in the town of Washington, North Carolina. So this is not Washington, DC, this is Washington, NC. This is one of the southern states. And then you can see the response in a well in this town. And you can see how the water level basically, in terms of meters below land surface, gradually drops as you go from late winter through the spring and summer and into autumn before it starts to recover. So this is a well hydrograph, analogous to a stream hydrograph, which we will see later, but we are plotting groundwater level instead of stream stage or stream discharge. But you can also see that there are individual peaks in the water level that are superimposed on this overall declining water level response, and they represent recharge events. So this is a relatively shallow well that even in the summer, sometimes can still receive recharge. So the previous diagram that I showed is kind of a simplification that basically recharge is favored in cool, wet periods and is less favorable in hotter, drier periods, but you can still have recharge occurring, for example, in the summertime. So then we can ask, how does recharge occur? And here we get into soil physics, Vadose hydrology, basically. So obviously it occurs through infiltration. Of course, not all water that infiltrates recharges the water table. As I mentioned, some of it can move laterally as interflow, the subsurface component of runoff, and some of it can be taken up by plants. You can even have direct evaporation out of the shallow soil zone. But to get recharge in general, you have to start with infiltration. So for an initially dry soil, the infiltration rate, which is in dimensions of length per time, so dimensions of velocity basically, will decrease over time as water is applied. And I will show this in the next graph. You can define a maximum or initial infiltration rate, and that is the F is the infiltration rate with a 0 or O subscript for initial. This infiltration rate is sometimes referred to as infiltration capacity. I avoid the term infiltration capacity because when I think of capacity, I think of a volume. How much can something hold rather than a rate? But as you will see on the next graph, sometimes the infiltration rate is called the infiltration capacity. So over time, after water is applied to an initially dry soil, once the application stops, the infiltration rate decreases from some value less than or equal to the maximum to a minimum or equilibrium value. And the infiltration rate at any time between the initial value and the equilibrium value, where the equilibrium value is F sub C, that infiltration rate at any time is F sub P. So this is the graph that I alluded to. This is from Fetter, another hydrogeology textbook, and you see what he labels as infiltration capacity. Just think of this as rate in centimeters per hour. F sub 0 is the initial value when water is applied, and F sub C is the limiting value, and the infiltration rate after initial application decreases asymptotically. Basically, it's an exponential decay curve. You have this function e to the minus kt toward F sub C. So at time 0, if you plug 0 into the exponent here, e to the 0 power is just 1. So you have f sub c plus f sub 0 minus f sub c. So your infiltration rate will just equal your initial maximum value. Conversely, if you say, let's let t approach infinity, then e to the minus an infinitely large number is going to be 0, 1 over a very big number. And so you have f sub c plus 0 times this product, which is just going to be 0. So at time sufficiently late, your infiltration rate approaches this limiting value f sub c. So I'm going to do what I did last night and pose some questions to you for you to think about for a couple of minutes. Again, I do this with my class. So we know that infiltration is going to be a function not only of the initial moisture content, but also of the texture. Like we talked about yesterday, with very fine textured soils, they tend to be lower permeability, like clay, for example. And so the infiltration rate in terms of initial capillary uptake into a fine-grained soil may be relatively high, but the ability of that soil to transmit water is actually pretty limited. So let's think about the previous graph. What happens if the rate of precipitation is greater than this initial maximum value, f sub 0? So let's go back to this graph. Let's say your precipitation rate or your rainfall is 11 centimeters per hour over a period of 4 hours, the period shown on this graph. So what will happen if rain is falling at 11 centimeters per hour? That's a pretty heavy rainfall rate, I know, for a period of 4 hours. In terms of infiltration, if you look at this graph and your rainfall rate is 11, will all of the water infiltrate? Will some of the water infiltrate? Will all of the water run off as overland flow? What do you think will happen? Okay, flooding. All right, David, do you want to just explain that a little bit more? What has to happen for flooding to occur?
My assumption, if the water doesn't flow into the soil, so the water will find another lower area. If it doesn't, so it become flooding.
Okay, so this is what I call rejected recharge. That is, some of the water will not soak into the ground. But if you look at it, say at time 0, if you think of the rainfall rate as being at 12, let's say, what will your rate of rejected recharge be, and what will your rate of infiltration be at the beginning? How much water is rejected or runs off overland, and how much infiltrates initially?
I would say the infiltration is 11, and the rest
is rejected recharge.
Rejected.
Exactly. So what that means is if you extend this across, then you will start out with 1 centimeter per hour of rejected recharge and 11 centimeters per hour of infiltration. And over time, that infiltration rate will decrease. And so after 4 hours, you will wind up with basically about 3 centimeters per hour of infiltration and about 9 centimeters per hour of rejected recharge. So everything above this line basically will run off as overland flow. Now, that scenario is a little bit simplistic, but that's a good place to start. Good. Okay. So we answered that question. All right. So the second question is, what happens if the rate of precipitation is less than F sub C? So let's go back up here. So F sub C is about 2.5 centimeters per hour. What happens if you have rainfall at 2 centimeters per hour over this 4-hour period? Does the water infiltrate? Does it run off? Does some of it infiltrate and some of it run off? Okay, so Gananjar, all of the water will infiltrate. Exactly. So you are less than the minimum value. So all of the water infiltrates. Good. Okay, last question. What happens if the rate of precipitation is less than F sub 0, but greater than F sub C? So let's say our rate of precipitation is 6 centimeters per hour, and it's constant over a 4-hour period. What happens over that 4-hour period? Okay. Inundation, Dion. Okay, so Dion, what do you mean by inundation? Can you explain that?
So when the infiltration, you say it's 6 centimeter per hour, and then still there is more than I mean, after 4 hours, the infiltration still more than 2.5 centimeter and per hour. So it means still there is a inundation in the surface area.
Okay, good. That's correct after 4 hours. But what about after 1 hour, let's say? Do you think there's going to be inundation after 1 hour?
Actually, there is after 1 hour still there is inundation, but it will be decreased after 1, 2 until 4 hours. That's mean.
Okay. What I think the graph tells us is that if you're raining at 6 centimeters per hour, all of that is going to infiltrate until you hit about 1.5 hours. And then at that point, you will have intersected this asymptotic curve and you start to generate rejected recharge after 1.5 hours. And then you will start to have inundation or flooding, depending upon the slope after that. Again, this is simplistic. In fact, the rainfall is not necessarily going to be constant, and the shape of this curve may be shifted over time. But in this simple case, the 3 scenarios I've given you are if it rains hard enough, you start to generate rejected recharge or inundation or flooding immediately. If the rainfall rate is low enough, then it all infiltrates. And then in between, it will all infiltrate at the beginning, but after some time, the pores will be saturated at the surface, and therefore the infiltration rate will be less than the rainfall rate. And so you will start to generate rejected recharge. Okay, good, good. Any further questions about this? Okay, so we can ask the question then, why does the infiltration rate decrease with time? And I haven't given you the reasons. I've just said that there are 2 reasons. I've kind of given you a hint about one of the reasons. So what do you think is one reason that the infiltration rate will decrease with time? Any guesses? What did we say about the last scenario if it's raining 6 centimeters per hour and you get to 1.5 hours? The soil is saturated. You know, exactly right. So if the soil is saturated, then that limits the rate at which water can infiltrate. The second reason is a little bit more subtle. It has to do with the pore space itself being reduced, that is the volume of voids. And that can happen by compaction. It can happen by translocation of sediment, by alluviation, but it can also happen if you have clays that are high in a certain type of clay mineral, like smectite or illite, that can swell, can expand in volume when they become hydrated. So basically the pore space can be reduced either by sedimentation or by clay expansion, and that also can reduce the rate of infiltration. So when we talk about infiltration, we talk about 2 stages. The first one is called imbibition, and that comes from the word to imbibe, which literally means to drink. So like I'm drinking water, the soil is drinking in water. And the first part of that is that with the mineral grains in dry soil, you're still going to have some film of water, some limited amount of water that is bonded to the surface of the grain. Then as water starts to infiltrate, particularly if you're talking about soils with clods or aggregates, that water is absorbed into the micropores within the grains or within the aggregates. Excuse me. And then surface tension draws the water into the pores, and you get a meniscus, like the shape on a graduated cylinder, you know, a curved shape. And then finally, with the pores filling up, those meniscuses are destroyed and the water flows under gravity. So that's the final step of water intake or imbibition. At that point, the soil is saturated. And then the second step is drainage, vertically out the bottom of the soil profile. Okay, so let's revisit the vadosome. If you remember the definition of hydraulic head, we said it was H equals psi, which is the pressure head, plus Z, which is the elevation head, where Z is the elevation at the intake, like the bottom of the well, if the well is only open at the bottom, and psi is the height of the water column above that. And we said that by definition, at the water table, pressure is atmospheric, and we reference atmospheric pressure to 0. Above the water table in the vadosome, including the capillary fringe, the pressure head is less than 0. And there are other synonyms that are used in soil science to refer to this pressure head. Sometimes it's called the suction head, sometimes it's called the tension head, sometimes it's called the matrix potential. So one of the things that becomes more complicated in the vadosome is hydraulic conductivity. Even if it is isotopic, if it is constant at a point, if you have saturated conditions, once you become unsaturated, the hydraulic conductivity becomes a function of the moisture content, that is the percentage of water-filled pores, and of the pressure head. And these two parameters interact with each other. So at some value of the pressure head less than 0, so water is being held under tension. So you talk about a negative pressure relative to atmospheric. As the porous medium starts to drain to the second stage of infiltration, the hydraulic conductivity becomes less than the saturated hydraulic conductivity. What we've been calling K yesterday in the vadosome, we call K sat. Conversely, we're going the opposite way. As you are filling the pore space with water, as the volumetric moisture content approaches porosity, So with wetting or imbibition, your unsaturated hydraulic conductivity as a function of the volumetric moisture content or a function of the pressure head approaches the saturated hydraulic conductivity. And so if the volumetric moisture content is small enough, or if the pressure head is negative enough, then the hydraulic conductivity for clay, the unsaturated hydraulic conductivity is actually greater than the unsaturated hydraulic conductivity for gravel, which may seem counterintuitive because when we think about saturated conditions, we think, oh, of course, water moves more easily through gravel because it's got big pores than through clay because it has small pores. But if we think about unsaturated conditions, because of capillary attraction, the clay will hold the water more tightly than the gravel will. It is tougher, it is more difficult to drain the clay than it is to drain the gravel. So this is a representation of the unsaturated hydraulic conductivity. Call it again, K as a function of theta, the moisture content, but you also call it K as a function of psi, the pressure head. And so here showing the decreasing pressure head, you have hydraulic conductivity on the y-axis, and here at 0, that represents the water table, basically. And initially, the hydraulic conductivity is relatively constant as you decrease the pressure, as it becomes more negative for both the gravel and the clay. But then you get what's called air entry, where you start to desaturate the pores, and the saturated hydraulic, or rather the unsaturated hydraulic conductivity now of the clay decreases, but not as much as the gravel does. So the way this manifests itself, the way this happens in the vadose zone, is you can have a capillary barrier forming where you have fine-grained sediments overlying coarse-grained sediments. And if you have kind of a sandwich, if you have like sand or gravel above clay, above sand or gravel, that's how you can get a perched aquifer, because the clay is saturated and then you have water building up, mounding above the clay, but below the clay, because of this capillary barrier effect, it's still unsaturated. So we can then write an unsaturated zone form of Darcy's law using chain rule differentiation. So again, we're defining hydraulic head as the sum of the elevation head and the pressure head, and putting this in one-dimensional derivative notation, we just say Q, the groundwater flux, equals K times the hydraulic gradient. And in this case, the hydraulic gradient, instead of being delta H over delta L or DH over DL, we're specifically for the unsaturated zone saying that L is in the Z direction. We're talking about a vertical coordinate system. Water is mainly just flowing vertically downward. So we say little q, the groundwater flux, equals the hydraulic conductivity times the vertical hydraulic gradient. And then we can, writing the unsaturated zone hydraulic conductivity as a function of the pressure head, we then say the groundwater flux, or the water flux, really, it's not groundwater anymore, it's soil water because you're in the vadose zone, equals the derivative of H, which is this sum Z and psi, or psi and Z, over dz. And so you're using dz in two ways here. dz is the change in the elevation head, but it's also the change in the vertical coordinate, because they're basically the same thing. And so once you do your chain rule differentiation, you wind up with K times dz over dz plus K times d psi over dz. And so ultimately, if you have one-dimensional flow downward for saturated conditions, in other words, you start out with unsaturated conditions and then water is taken in by the soil. At some point, you are going to wind up with your limiting value of the unsaturated, of the water velocity through the unsaturated zone is just being equal to the hydraulic conductivity. So the water movement in any case winds up being independent of elevation. So you approach a steady state value of water movement as you approach a steady state infiltration rate. All right, so again, that's what I was saying. If psi is constant, if your pressure head isn't changing, then your water flux equals the unsaturated hydraulic conductivity. And so you wind up with your steady state infiltration rate as equaling the saturated hydraulic conductivity. And then again, ultimately, until you add more water back to the system by rainfall or by irrigation, then that steady state infiltration rate is not going to be exceeded. Okay, so let me show some examples then from work that I did in Texas. I showed a map of the water table in the Southern High Plains region of Texas yesterday in the last class period when I talked about mapping the water table. Well, this is what the land surface looks like above the water table. And you have these ephemeral lake beds, which means that they are not filled with water year round. They're only filled with water during the wet season after rainfall, or perhaps if there is irrigation and water is running into them. And this cropping is mainly for grains like wheat. And when the lake beds are dry, the floor of the lake is actually dominated by a type of clay called a vertisol, which consists mainly of the clay minerals that I talked about, like smectite and illite, that expand when they're wet and crack or contract when they're dry. And this coin here is US quarter, so it's about 2.5 centimeters in diameter. So you can see that you have small pores, but you also have larger, what we call desiccation cracks. And when the lake bed fills up, it becomes revegetated with grasses, and these cracks tend to close up, but you still have roots of plants taking advantage of the cracks as preferential spaces to grow. So you can have preferential flow paths associated with infiltration. So in a cross-section view, this is from a paper that I published on some of my work there, what you have is rainfall, and if the rainfall is not large enough to generate infiltration, then basically that water will be lost by evaporation. Or if it is large enough to generate infiltration but doesn't really generate runoff, then you can have some infiltration, but then the water is transpired. If it is large enough to generate, the rainfall amount is large enough to generate rejected recharge or runoff, then you may have water accumulating temporarily in these dry lake beds and these playas, and then infiltration occurs beneath these playas. You can also have irrigated agriculture, as I mentioned, and so you can have irrigation return flow, which contributes to the runoff to these playas and the infiltration beneath it. And in some instances, there are drainage ditches, and so there is infiltration beneath these ditches. Well, if you have a perching layer, like a clay layer, as I mentioned, what can happen is you can have mounding and you can have a perched aquifer forming that is discontinuous from the main water table aquifer. And this can basically become a steady state condition where the rate of resupply of groundwater moving downward through the vadose zone to the perched aquifer is balanced by the rate of leakage out the bottom of the perched aquifer. So you're at a steady state and you're maintaining this discontinuous zone of saturation. This is just a map view of the previous kind of conceptual diagram cartoon. And there are two sets of contour lines here. So the main water table in the High Plains Aquifer is shown in the narrower line, and the contour interval is 3 meters. And so you can see that the hydraulic head decreases to the northeast. So your flow in the regional aquifer will be to the northeast. But in the perched aquifers, you can see the hydraulic heads are higher than in the regional water table aquifer. So you have a mound here with a hydraulic head of 1,006 meters above sea level, then 1,003, then 1,997. Whereas beneath that, I haven't contoured it because it would get too cluttered and confusing, but you're at like, 962. So you're potentially 35 meters distance from the perched water table to the regional water table. So basically you are looking at a top-down view of two different water tables, one perched, lying some distance above the other. So that's part of the reason why I said yesterday, when you are doing water table maps, it's important to know what aquifer you're in. And in this case, you're looking at two different aquifers. So these playas, in fact, become areas for focused infiltration and focused recharge. So instead of having, if you think back to the map that I showed yesterday, a recharge zone at the up gradient end of the aquifer and then a discharge zone at the down gradient end, that may be true, but in between you've got all these dry lake beds that when they fill with water will cause infiltration down to the water table. It's kind of like a shower head, basically. You have a shower head over a bathtub, really, and that shower is causing water to come down at different locations under these playas. Okay, so that gets me to groundwater stream interaction. So I've talked about infiltration and about recharge. Let's talk about some about discharge as well as recharge in a different way. And somebody asked me about this last night, and I promised I would talk about it today. So we can talk about streams and their relationship with groundwater based upon whether the stream is losing or gaining. So a gaining stream is like the first diagram that I showed. So I'm going to go back up all the way to that first diagram. This would be a gaining stream because groundwater is discharging to the stream. But you can also have a losing stream where water infiltrates beneath the bed and the stream recharges the aquifer. Now, losing streams are often seen in arid environments, but not always. You can have losing streams or segments of losing streams in humid environments as well. And in fact, streams may be gaining along one part of their bed and losing along another part, depending on the geology and the geomorphology. A special case of a losing stream is a disconnected stream, where the stream actually does not intersect the water table, but you have infiltration beneath the stream bed and the water table is some depth below that. And finally, you can have an isolated stream, which is neither gaining nor losing. If you think of a lined irrigation ditch, like a concrete channel, that would be like an example of an isolated stream. But you have water moving within the channel, and you may have evaporation from the channel, but you don't have water infiltrating from the channel or groundwater discharging to it. The next several diagrams, including this one, are from a really good free online US Geological Survey publication from 1998 called Groundwater and Surface Water, a Single Resource, which talks about the interconnections between groundwater and streams and groundwater and lakes. And you can see here the example of a gaining stream where the flow direction is toward you and the water table intersects the stream. And in the opposite scenario here, the stream intersects the water table, but the flow lines are away from the stream. So you have infiltration beneath the stream. This third scenario is what I talked about with the disconnected stream as being a special case of the losing stream, where the water table is beneath the stream bed, but you have a mound on the water table representing infiltration beneath the stream. In terms of gaining and losing streams, streams can be gaining in some locations and losing in others, as I mentioned. But even at a particular location, a stream can be gaining at some times and losing at others. And this is going to be a function of physiography, that is topography, really the shape of the landscape. It's going to be a function of transpiration, of seasonal wet and dry periods, and storms. So let me talk about transpiration for a minute. If these plants indicated here were actually trees and their roots intersected the water table, you can imagine that the trees would function in some sense like the well that's being pumped in the first diagram that I showed, that they would cause water to move away from the stream. In effect, they would be pumping water from the stream by transpiration. So there are some plants in the riparian zone along streams that are capable of doing that. In terms of seasonal wet and dry periods, really that has to do with how quickly the water table responds to changes in stream flow and changes in or amounts of precipitation. But what I want to concentrate on most is this final case of bank storage, where you have the stream and the water table responding to runoff associated with storms. So if you have a stream that is normally gaining, but you generate runoff, and the runoff may not even be local, it may be from upstream some distance, then the water level in the stream will respond more quickly than the water table. So basically what will happen is that the stream stage will rise and the gaining stream temporarily becomes a losing stream. And then the stream stage will fall more quickly than the water table. And so you will have the water that was stored, if you will, river water or stream water that infiltrated temporarily going back into the stream channel. And that can have some interesting chemical implications in terms of the potential for reactions between solutes that are in the stream water and minerals or organic matter in the stream bank sediments. So this is a generic stream discharge hydrograph. And on the top axis is, top x-axis is just showing precipitation. And on the y-axis is shown discharge on a log scale, although there are no numbers, it's qualitative. And on the bottom x-axis is shown time. And so you can see that the stream responds to precipitation. Now, some of the water that is generated is overland flow, but a lot of it is actually water that is displaced from soil pores on hill slopes by newer water infiltrating in sort of a piston displacement. But you can also have relatively rapid bypass flow, like interflow as well. So anyway, all of this runoff, whether it's overland flow or interflow, causes the water level and thus the flow rate or the discharge of the stream to respond more quickly to rainfall. And then the water table response lags behind that. All right, so we can classify streams as well by flow duration. And these include perennial streams, that is streams that flow year round. If any of you are gardeners, you may be familiar with perennial plants as opposed to annuals. Annuals you have to replant every year. Perennials rebloom each year. So perennial just means through the year, all the time. Intermittent is a stream that flows only seasonally, whereas an ephemeral stream is one that flows temporarily only after storms. So if you look at these three categories, which of these types of streams is likely to be a gaining stream, and which type or types is likely to be a losing stream? Any guesses? Okay, so Panji, gaining perennial, losing intermittent and ephemeral. Excellent. Yep, that's exactly right. So let me show some examples of these. All right, so this is an ephemeral stream in New Mexico. This type of stream in the Western United States is called an arroyo, A-R-R-O-Y-O. That's a Spanish word. This was a part of the USA that was originally settled by Spanish colonists. And you can see the stream channel here is sand, and there's some gravel along the bars and along the banks. And it's not uncommon in arid environments for there to be these kind of dry stream channels where flow only occurs after a storm and the water infiltrates relatively rapidly. But if you look at the vegetation along the banks, there must be enough water supplied. This may be a disconnected stream. It's probably not intersecting the water table, but there's certainly enough water supplied through channel transmission losses to sustain the vegetation in the riparian zone along the banks. This is a discharge hydrograph for an ephemeral stream in Arizona, which is the next state to the west of New Mexico. So Arizona is between New Mexico and California. This is the Little Colorado River near Cameron, Arizona. This is close to the Grand Canyon. And if you think back about this conceptual storm discharge hydrograph, often you will see discharge on a log axis. So it will be a semi-log graph. But in this case, this is actually an arithmetic axis. And the reason it's an arithmetic axis is you can't depict zero on a log scale. And so for some period, some weeks after rainfall, the river flows and then it stops. And then there's some more rain and it flows and stops. And then again, it flows and stops. So this is what a hydrograph looks like for an ephemeral stream. And I will say one of the great things about the US Geological Survey also is there is a national network of like 7,000 stream gauges, multiple gauges in every state. And this is an example of one of them. And you can go onto the US Geological Survey website and select a gauge and download the discharge hydrograph or the stage hydrograph for that gauge for whatever period of time that the gauge was operating. All right, somebody was asking also last night about what the water table map looked like for a gaining stream or for a losing stream. And that's shown here. Again, this is from Heath's Basic Groundwater Hydrology. And so for a gaining stream, you have your equipotential lines making a V shape with the point of the V pointing upstream. So this is comparable or analogous to what we talk about with topographic contour maps and the rule of V's, where the topographic contour V's upstream. In this case, for a gaining stream, the equipotentials V upstream. That is, again, we're assuming the flow lines are perpendicular to the equipotentials. We're assuming isotopic hydraulic conductivity, that hydraulic conductivity is constant at any point, although it may vary point to point. And we've got these flow lines converging toward the stream. Well, if you look farther downstream for a losing stream, the opposite is true, that the flow lines diverge away from the stream and the equipotentials have the V shape with the tip of the V pointing downstream. So again, equipotentials make a V shape pointing downstream for a losing stream, make a V shape pointing upstream for a gaining stream. And you can infer the flow lines based on the equipotentials. I mentioned the riparian zone. The riparian zone is just the zone along the bank where you may have vegetation. And at a regional scale in a groundwater basin, you can have both shallow and deeper groundwater discharge coinciding along the stream. But also along the stream, you can have something called the hyporheic zone, which is a little bit different. So the riparian zone is shown here with the trees and the shrubs. The hyporheic zone is actually the groundwater surface water mixing zone. So you can think about going down a stream and groundwater, or rather stream water, infiltrates into the bed of the stream along part of the stream and then moves horizontally within the bed and then comes back up again. And where it is moving within the bed for a gaining stream, it is mixing with the groundwater that is discharging. And this is a biochemically or biogeochemically reactive zone that we call the hyporheic zone. And people who work on stream ecology pay a lot of attention to the hyporheic zone. So looking at the hyporheic zone another way, if you have a pool and riffle stream where the pool is the deep part and the riffle is the shallow part, you may have water going downwelling into the bed at the head of the pool and then coming back up at the downstream end of the pool at the riffle. You can also have water moving laterally out of the stream channel and then back into the stream channel. So the groundwater kind of mixes with, again, for a gaining stream, this water that is moving into and out of the bed and into and out of the banks. If you have a stream that meanders, you can have water moving not just within the channel, but infiltrating and moving across this meander cutoff. So as noted here, surface water exchange with groundwater in the hyporheic zone or the mixing zone is associated with abrupt changes in stream bed slope and with stream meanders. Okay, so I'm through with streams for right now. I'm about to get into lakes. Any questions before I talk about lakes?
Anyone,
Okay,
please?
yeah.
Maybe Professor Alat, regarding the K itself, can you show us a previous slide?
Sure.
That one.
This slide or the one before that?
Yeah. I know. I still guessing how the groundwater can access to the. Is that possible when the river become more dry? The groundwater was sucked water from river body to infiltrate the water, become and move to the groundwater. And
yeah, so seasonally you can have a stream drying out, or you can have the water table falling and a stream that is gaining during the wet season during the dry season may become a losing stream. And in fact, the water table may fall beneath the bottom of the stream bed. And then during the wet season, the water table may rise back up again and it becomes a gaining stream again.
Ah, I see.
Does that make sense?
Yeah, but is that influenced because how do you say if it's also climate take a part too to make the movement of the groundwater too?
Yes, because the groundwater for a gaining stream, you know, let's assume is being recharged on hill slopes away from the stream. And so if you enter a drought or a dry period, then that water table may drop because you are not getting as much infiltration, you're not getting as much recharge. And if in fact the stream has its headwaters in another area, it's possible that the stream could continue to flow even as the water table drops, because the water table is perhaps affected by the local geology, whereas the stream may be, you know, a long way from its headwaters. So let me go to the previous slide. So let's use this left-hand block diagram as an example. Let's say that this local area contributing water to the water table and base flow to the stream dries out, so that the water table falls. But let's say the headwaters of the river up here in the mountains somewhere, maybe the river will continue to flow, but this section of the river, this reach, becomes a losing reach instead of a gaining reach.
I see. Thank you for your explanation.
Sure. I hope that makes sense.
Yeah.
All right. So we can talk about lakes and groundwater interactions with lakes, much like we do with streams. We can have gaining or inflow conditions, and we can have losing or outflow conditions. And the term we use for lakes that intersect the water table are called seepage lakes. Whether you receive inflow, in effect, this is like gaining, or whether you receive outflow, this is like losing. Either way, this is called a seepage lake. It's just, if it's gaining, it's an inflow lake, and if it's losing, it's an outflow lake. And you could potentially imagine a situation where you have through flow as well, where maybe you have topography that is on a regional slope, but it is like a sine wave. And so maybe you have an outflow lake up the slope to the right, and then you have an inflow lake down the slope to the left, and in the middle you have a through flow lake, such that some of the water passes into the lake and then back out as it's following the regional slope, and some of the water actually passes beneath the lake. So this next diagram actually shows something like a through flow lake. This is another diagram from Fitz, and this is kind of nice because it shows both a gaining stream and a pond or a small lake that is feeding it. And so the equipotentials here are shown 153, 152, 151, 150, and water is basically passing down the regional slope, and the pond affects it a little bit, but not much. And this stream that is coming out of the pond really isn't either a losing stream or a gaining stream. You don't see the water table being affected by the presence of the stream. But once you get from this smaller tributary stream to the bigger stream, all of a sudden you can see that's the regional base level. The water that is moving down slope from either side of this stream is converging toward this stream. So this is a through flow lake in effect and a gaining stream. I'm thinking for a minute about Indonesia and perhaps the Philippines as well. When you're thinking about volcanic lakes, crater or caldera lakes, those are probably likely to be outflow lakes because they are at higher elevation. And to the extent that the volcanic rock in the volcano cone itself is fractured, or to the extent that you have loose ejected rock, like tephra, then you may have flow originating in the caldera lake and then moving radially away from it down the slope. Okay, the next case I'm going to talk about, which is one that is particularly important in Kentucky, but also applies to some extent in parts of Indonesia and certainly other parts of Southeast Asia, is karst. And karst forms, like I mentioned yesterday when I showed the picture of the limestone sample, when the minerals in limestone, mainly calcite or calcium carbonate, react with rainwater or groundwater or stream water that is mildly acidic, that contains dissolved CO2, so carbonic acid, kind of like club soda, like in a soft drink that fizzes. That acidic water is going to react with the rock, and it will preferentially flow where there are already holes in the rock or cracks or fractures in the rock, and it will dissolve away the rock along those flow paths and make them bigger. So you get what we call sinkholes, or ponors is a European name. And so these are kind of like the playas that I showed on the Southern High Plains. They are low spots on the landscape where infiltration is focused, but the infiltration moves along these enlarged fractures or pathways where the rock has been slowly dissolving away. So you can get relatively rapid infiltration, what is called here quick flow, or you can have infiltration that is more diffuse, more spatially distributed, that we call intermediate flow. And then finally, in the rock matrix, it slows down and becomes slow flow until it hits the conduit. And this is like a cave system. So Jadfan, if you remember when we went to Gunung Walat, I think, which was in the IPB forest with the cave. This is like that. This is basically a hole, but it's below the water table. So it's going to be completely full of water. And then the outlet, the discharge zone, is actually a spring, an area of concentrated discharge. And so these are maps that I took from a paper by a group at another of the universities in Java, and I can't remember which one. But they are working in an area southwest of Malang. And I know there's karst close to Malang as well. This is the Jangrangan, if I'm saying that right, karst. And these karst features are basically on the flanks of volcanoes. These, like at Gunung Walat, represent like uplifted atolls, if you think of Pacific islands that had fringing reefs around them. And then when this became a bigger island in the limestone that the coral made was uplifted, then it became subject to weathering and dissolution. And so karst forms. And that's shown in detail in this next diagram. So the Jangrangan formation is all this limestone, and a symbol for limestone is usually this kind of brick pattern. And you can see the springs shown in the circles with the plus signs, and you can see the caves. And recharge occurs where you have sinking streams. And in this instance, the sinking streams in some places occur where you've got water flowing off the volcanic rocks and coming into contact with the limestone, and then it sinks and comes back up at a spring. So the water is being diverted underground, but to some extent, it's like underground stream flow. So in Kentucky, what this looks like, and this is just a kind of a cartoon, a block diagram drawn by one of my colleagues, you have on the surface a topographic divide, and you can have a sinking stream, and it may disappear like in the previous diagram here, going into a sinkhole. or a swallow hole. And then that water may flow as a stream within a cave. And you can have sinkhole ponds, again, sort of like the playas that I showed on the high plains where there's infiltration beneath them. And then you can have a base level or blue hole spring. One of the key points here to note, and I mentioned this briefly last night, is that in groundwater systems, sometimes you can have water flowing from one surface watershed to another. So you see the regional flow path is under the topographic divide. So it's interbasin flow. This is a picture of the classic sinkhole plain near Mammoth Cave in southwestern Kentucky. So you see this really kind of undulating landscape and not much surface drainage. Most of the drainage is below surface, and occasionally you'll see ponds. Some of these low spots are dry. Others, there may be clay soil at the bottom, so it holds the water better. So again, kind of reinforcing the point that watersheds and groundwater basins may not completely overlap, may not coincide in karst terrains. This is a map from my area, the city of Lexington. And I want you to note, first of all, the surface watershed for this stream marked in yellow called Cane Run. And this is an ephemeral stream, so it flows only after rainfall. And its outlet is here at Elkhorn Creek. And if you look, you see these little black triangles, and each of these represents a sinkhole, or what's called a swallet, in the bed of this dry stream channel. And so these are points where water running along the stream will infiltrate and be diverted into the subsurface and will go to an underground stream channel like this or like this. And the difference between the two diagrams I just showed is this is what we call pipe full. It's completely filled with water. Whereas this has the water table basically coinciding with the stream in the cave. And this is perhaps a poached aquifer. So you can have very discontinuous zones of saturation within a karst system. So if you look on the right here, this green line is the outline for the groundwater basin. So it mostly is the same as the surface water basin. It's a little bit different in here, but then if you look to the northwest, you don't see any more of the little black triangles. Basically, you don't have any more of the stream bed sinks here. That line of sinkholes follows a regional kind of fracture trend, regional stress trend, southeast to northwest. And it aligns with the presence of this quick flow zone, which has got the conduit underneath it, which emerges at Royal Spring. And this is a picture of Royal Spring. So that's where this underground, basically pipe, if you will, this natural limestone pipe comes back up. And this is actually the water supply for, pardon me, for the town of Georgetown here. Okay, so this is another conceptual diagram showing flow along Cane Run. This is from colleagues at the Kentucky Geological Survey. So during the dry season, basically you have water flowing along the channel and it gets diverted into the subsurface. And during the wet season, you have flow occurring at a higher rate over a greater distance. And this diagram is actually, we know now, not correct, that even in the dry season, this underlying conduit is completely full. But basically you get focused infiltration coming down through these holes, so-called swallow holes in the stream bed. This is a photograph of a limestone outcrop near Mammoth Cave, Kentucky. Mammoth Cave is one of our national parks. It is the longest mapped cave system in the world with about 800 kilometers of interconnected mapped passages. This is the former park hydrologist, Jim Quinlan. This is a picture I took about 30 years ago on a field trip. But what I want you to note in the outcrop is just how weathered this limestone is. So if you remember the picture that I showed you yesterday of the limestone in a hand sample with a hole in it, you basically see this at the outcrop scale. So you can see how rapidly infiltration could be focused through these holes, as well as along solution enhanced bedding planes or stratigraphic contacts. So this picture was taken above the sinkhole plane upslope from this plane that I showed you. And this is a water table map. It actually says potentiometric contour, but these are really equipotentials. These are water table contours for the Mammoth Cave region. This is a classic map. This is the extent of Mammoth Cave National Park. This is the city of Bowling Green. The Barren River and the Green River are the regional base level in the region, and so flow converges toward them. You can see the swallow holes, swallowette of the sinking stream. You can see different groundwater basins have been defined. But if you compare this with the water table maps that I showed yesterday, this is so much more complicated. You get basically these subsurface dendritic drainage networks that look like subsurface stream networks. And in effect, they are, but you can also get interbasin flow, kind of back to what you were asking earlier, Jadfan, about seasonal variability. When the water table rises up high enough, it can spill over in the subsurface from one of these stream networks to a different stream network. So even though they've mapped the equipotentials, you can see that these almost function like drains. And this is a really complicated setting. So mapping groundwater flow in karst terrains is much more complicated than in a more conventional sand or gravel or rock aquifer. And basically to do a map like this, this represents years of data collection and a lot of what we call tracer tests. So more about tracer tests in a moment. So one of the things that's distinctive about karst springs is how quickly they respond to rainfall. And so this is a discharge hydrograph. A discharge is shown on the y-axis on an arithmetic scale, and it's shown on the right-hand y-axis in order to show multiple variables. So in addition to discharge, we're showing electrical conductivity, which is a measure of total dissolved solids. And on the left-hand y-axis, we're showing precipitation, which is these blue bars on the bottom in millimeters, or the water temperature. And so the really interesting thing about this is to see that the water discharge, the gray, which is correlated to the water level, responds, that is the flow of the spring, responds to precipitation and rapid infiltration. So you see rainfall, you get a spike in the discharge. You get more rainfall, you get more spikes in the discharge. It responds really quickly. But note that the electrical conductivity also responds, that as the discharge goes up, the electrical conductivity, the total dissolved solids, goes down. And if you look at the water temperature, as the discharge goes up, sometimes the water temperature responds, sometimes the water temperature goes up, sometimes the water temperature goes down. So can anybody speculate about what you think might be happening to cause the temperature or the salinity to change as a result of precipitation? I mean, it makes sense that the flow rate would change when you have infiltration, but why would the electrical conductivity change, or why would the temperature change? Okay, comment in the chat. Maybe the rainwater temperature is higher than the groundwater. Yeah, so in the summertime, the air is warmer than the groundwater. Groundwater temperature is relatively constant year round. You can see in this case, it fluctuates Seasonally, it's a little bit out of phase with the seasonal change, but it only varies within a couple of degrees Celsius. But after a storm, it may vary by several degrees Celsius. So in the summer, the recharge is warmer. In the winter, the recharge is colder. In terms of the electrical conductivity, what happens is the runoff is coming in, and the runoff is relatively dilute. There's not much dissolved in the rainfall that hits the ground and infiltrates. And so basically you get more dilute water, so it drives down the electrical conductivity, and then the water seeps back out of the rock. So this is analogous to what I talked about with bank storage in a stream, that in a karst conduit, you get water moving through the conduit with storm flow, and it pushes the water that was in the conduit out, but it also pushes some of it into the rock around the conduit. And then as that pressure pulse recedes, as you get recession on the discharge hydrograph, then you get the hydraulic gradient reversing, so that conduit then becomes gaining again, and you have water seeping back out of the rock into the conduit. Now, there are a couple of exceptions here where the electrical conductivity goes way up in the wintertime. And the reason why, and Faisal probably remembers this from Colorado, is in places where you get snow or ice on the roads, they put salt on the road to melt the snow or the ice. And as a result, if you've had snow or ice and salt is applied to melt it, because you don't want to drive on the ice, you'll skid and wreck your car. Then if you have rainfall coming through, if it starts to warm up, then that will flush that salt with the runoff. So you'll have basically non-point source pollution coming in with the salt. Okay, so let me wrap up then with the last few slides and leave a couple of minutes for questions, just talking about how you estimate recharge and discharge. And this is from a great review paper from Hydrogeology Journal in 2002 by Bridget Scanlon. And there are a lot of different techniques, and some of the techniques differ between arid and semi-arid climates on the one hand and a humid climate on the other hand. But basically they break down into physical methods such as water budgeting or seepage meters, or looking at heat exchange, chemical methods like isotopic tracers, and numerical modeling. And then in the unsaturated zone, this is basically recharge estimation. You can use lysimeters, you can do Darcy's law calculations. So Bridget's paper is actually about estimating recharge, but some of these techniques using watershed modeling and isotopic tracers and discharge, seepage meters, you can actually use for estimating discharge to streams and lakes as well. So let me just show you a few examples. So this is one of my former students, Obajit Mukherjee, who's now a professor at Indian Institute of Technology, Kharagpur, and he is gauging flow at a particular transect across this stream. And Faisal and Jadfan, you probably remember when we did this near Bogor. We were measuring stream flow. So if you measure the stream flow, basically you measure the velocity at multiple points across the stream, and you measure the depth, and you know the distance between your measuring points, you can integrate this. It's like integration by parts. And then you wind up with a discharge measurement. And if you then take a stream flow measurement at a different point along the stream, downstream, and it's higher, then that means it's a gaining stream. And if it's lower, that means it's probably a losing stream. Okay, and then a seepage meter. This is a picture of me standing on a seepage meter. So it's basically a barrel cut in half that's put over a seep or a spring, and you measure the rate of water flowing out. That's actually that same stream. This is in the summertime looking upstream. This is in the wintertime looking downstream. So Abhijit would have been right here. You can do Darcy's law calculations. If you remember when we talked about vertical hydraulic gradient, you can calculate the vertical hydraulic gradient such that this would be an example of an outflow lake or a losing stream, because the water level, we're assuming this is hydrostatic, above the datum, it's going to be constant within the water column. So the stream elevation is here, and the head in the piezometer or the monitoring well is here, and the distance between the water in the surface water body, and groundwater is this vertical distance here. So you have the head in the surface water, or the stream, minus the head in the well or the piezometer, divided by the depth of the piezometer below the bed. And so you can do a Darcy's law calculation there if you know the hydraulic conductivity. And in this case, you may not know the magnitude, but you know it's downward because the stream is higher than the water level inside the piezometer. And then this is just a picture of me doing that kind of measurement in a reservoir. We can look at thermal fluxes. These warm spots in January coincide with the same color scheme with the cool spots in August. So this is basically winter and summer. You have the same kind of so-called anomalies, 12 to 15 degrees Celsius. These are where our seeps are. And you can calculate one-dimensional fluxes that way. Vadose zone environmental tracers, tritium, the historical input function of tritium from nuclear testing. Chloride, you can do chloride mass balance, chloride and rainfall. In karst terrains, you can inject dye into the subsurface. And that's it. And despite my best efforts, I am exactly at 1:30 again. So let me stop. For those people who have to go, please feel free to go. For those people who want to ask questions, I will stick around. Again, I realize it's Friday. Some of you may have labs. So that's the end of this set of slides, and I will pause there.
Please, if you have question, student or college, maybe, if you have question, you can directly deliver your question to Professor Alan.
So
If
I will
you
say
have-
that.
Oh, yes.
I'm sorry, Jonathan.
Please, Professor Alan, continue.
I was just going to say that map that I showed of Mammoth Cave with all those underground streams, a lot of those were traced by injecting dye and then seeing where the dye came out. So that's what we call a tracer test. So it's basically a measure of how the discharge point, the spring, is connected to the recharge point or the sinkhole in a karst terrain. That's it.
Anyone want to ask to Professor Alan?
And again, Jadvan has my email. If you have questions later you would like to ask by email.
May I, Pak Jadvan?
Yeah, go ahead.
Please.
Okay, yeah, thank you very much. Professor Alan, in one of your slides, you explain about type of rivers, which are perennial and intermittent and ephemeral.
Yeah.
And I'm very much sure that there is a possibility for a river to change or to convert from perennial to intermittent or ephemeral, or conversely from intermittent to perennial. My question is it possible to recover a river, for instance, from intermittent to or ephemeral to perennial? And do you have any idea how long the recovery period will take in average?
Well, by definition, perennial means that it always flows. So I would say the way to convert a river that always flows to one that does not always flow, perhaps, is to put a dam on it. And conversely, if you have a river that is dammed and you take the dam out, that may convert the downstream portion from being intermittent or ephemeral to being perennial. But typically when we say perennial, that means that it's always going to flow unless you have some sort of, I guess, catastrophic change. So for example, one possibility is if you have in a mountainous region an earthquake or a landslide that causes what we call a landslide dam or an earthquake dam that basically blocks the flow of that river. And for some period of time after, the river may not be perennial. And then ultimately, because it's just a rock fall dam, that dam may fail. But I can think also of hypothetical scenario where you have a river that has relatively low discharge. And if you put a dam on that river to create a reservoir, and then if you're pumping water out of that reservoir, for example, for irrigation, then you have changed the flow regime and that river may be no longer perennial. Does that make sense?
Yes. Because I think that it's really related with the condition of our watershed in the upstream side. So if we change the watershed, it will influence the river flow in downstream area. Is that correct?
Yes.
Okay.
I agree.
Yes. Actually, I have one question more.
Sure.
Okay.
Sure.
Yes, please.
Yes, I'm very interested with base flow, Professor.
Okay.
River base flow.
Okay.
Yes, I think that's very essential to sustain the river flow in the dry season period. Is it correct if I have an argument that river base flow hydrograph, if we concerned with the river base flow hydrograph in our research, is that similar with the river hydrograph during dry season period, Professor?
Yeah, I would say, again, unless there are human interventions in the flow of the river, that during the dry season, if the river is perennial, the only flow that will be in the river is base flow. So by definition, your river hydrograph is going to be a base flow hydrograph because there will be no contribution from runoff.
Okay. Okay, thank you. Because I really concerned with the river base flow because people never focus on river base flow. They focus on the flat high discharge. Yes, they forget about the river base flow. It's very interesting topic.
River base flow is important for ecological reasons, for sustaining stream ecosystems. It's also important if you have wastewater being discharged, the base flow dilutes the wastewater that is coming into the river as well. So it can limit the impact of pollution potentially.
Yes, correct. Thank you. Thank you very much. Very good.
Thank you.
Yes.
Okay. Are there any other questions?
From Faisal, I think. Please.
Okay, Faisal.
Yeah. Do you still have time?
Sure, of course.
Yeah, thank you.
It's okay.
Yeah, thank you. So thank you for the awesome presentation. I really enjoyed it. I have a question. So speaking about the intervention or interaction between the surface water, groundwater, and human interaction, or anthropogenic sources. So, for example, if you want to quantize the amount of effect of human interaction in a surface or groundwater basin, how do you start? For example, if you want to study groundwater and surface water interaction with human activities in, for example, Malang City, do you have any view of how do you start the maybe a decade-long research? Thank you.
That is part of what I have been thinking about in terms of karst hydrology. Let me go back up a few slides here, looking at the karst hydrology in Lexington, because we have basically storm sewers, and if they are not working properly, if they're leaking, we have sanitary sewers that exchange water and potentially exchange pollutants with the surface channels and with the subsurface flow paths. And so part of the challenge is being able to meter the anthropogenic impact. So if I go back to my first slide at the beginning with this conceptual diagram, this conceptual diagram is showing pumping as well. And so if we were able to put a meter on every pump, then that would be great. We could quantify withdrawals, but as I'm sure you know, trying to do that in terms of agricultural pumpage, either groundwater pumping or just surface water diversions, I suspect Indonesia is like America, that there are a lot of places where that's not measured. And so you have to make estimates of what the pumping rates are, either of surface water or groundwater. So I think the first challenge, the first approach is just mapping your flow systems and figuring out what your potential locations of inputs and outputs are, and then trying to quantify them such that if you're looking at a gaining reach of stream, going back to base flow can be artificially supplied, not just by irrigation return flow or by, but by storm sewers as well. And so if you can quantify the anthropogenic inputs or outputs to the system, then that goes a long way toward being able to close the mass balance. But that's a very challenging exercise.
Thank you. I get your point.
Yeah, sorry, I don't have a better answer for you.
No, I mean, I get the point. It's a long journey, but yeah, I think by first mapping the system and then maybe one step by step, quantifying the amount of
right, selecting
output,
representative subbasins or subwatersheds, and then seeing if you can indirectly estimate fluxes by household water use or something like that, or industrial or agricultural water use. But it's a challenge. And I mean, you came out of one of the best programs in the world for that sort of thing at CSU. So, I'm sure you were exposed to people there who have thought about these issues a lot more than I have.
Thank you.
Great, thank you.
Thank you
Any other questions from anybody? Just
Maybe-
kind of, go ahead, Jatan.
Oh, sorry. I'm sorry to interrupting.
No,
maybe
that's fine.
one question again. One question left because I think time's up.
Right. We're 10
Unfortunately.
minutes over again. Sorry, I talked too much.
No problem, Professor. We are happy to listening your presentation because it's interesting and new knowledge for us because hydrogeology is quite new topic and it need to be concerned, especially for Indonesia because we don't have any mapping regarding the groundwater and catchment in groundwater, I think.
Yeah, and that's a critical first step is just groundwater mapping. And, hopefully some of the things that Adam talked about tie into that in terms of being able to use remote sensing to kind of infer data where you don't have wells, but individual on the ground point measurements wherever possible are really important.
Yeah. Maybe if no question from another, maybe I have, Aputu, please. He already raised his hand. Please, Pak Putu.
Okay, thank you.
Yes, sir.
Hello, Prof. Okay, thank you for the time. Jadi, your explanation is very interesting and very clearly. Yeah. I want asking about the technique for recharge or discharge estimation. There are several methods to estimation the recharge or discharge. Isotopes, isotope tracer as one model to estimate the recharge or discharge. What do you think about the uses of isotopic tracers for the interaction between surface water and groundwater, Prof?
I have been using a lot the stable isotopes of water, oxygen-18 and deuterium, and I debated actually about talking about that today, but I figured I would talk about it in next week when I talk about groundwater geochemistry, that I would include some information about isotope hydrology as well. Oxygen-18 and deuterium measurements are now becoming more routine in the United States, they can be done for as little as $7 a water sample. It used to be a lot more expensive. I realize, in rupiah, that's still a lot of money potentially, but it's a lot less expensive than it used to be. And there are technologies that mean that you can analyze a lot more samples. And so I'll give some examples of that next time, because that's something I've been thinking about, using water isotopes to at least qualitatively estimate recharge in different terrains. So,
Okay.
yeah. So next Wednesday night for you, next Thursday morning for me, we'll talk about isotopes.
Okay, thank you for the information, Prof.
Yes, thank you.
Thank you.
So that's a good transition to what I'm going to be talking about next week about groundwater chemistry, including isotope hydrology and some about contamination. So again, I'm happy to take any other questions, but if people need to go, that's fine too. I wish everyone a happy Friday and a good weekend.
Okay, I am so sorry, Professor Alan. I think the time is.
Oh, not a problem. No, you all have been very patient with me.
Yeah, I will collect the question from the student and give some time to the student. Maybe if they read again your presentation, maybe they have some question. I still wait for a question, or maybe comment also, and I will send it maybe after the class or before the next class in the Thursday.
And I'll be happy to take time to answer them.
Yeah, I still wait from the student. Maybe they still read again and maybe seeing for the other literature to regarding for their question maybe. So I think we need to wait the student also to think about their question.
Okay, great. Well,
thank you very much,
everyone.
Professor Alan, and the other student, participant, colleagues, and others. Maybe before you can leave or we leave this class, I think maybe we can take a picture.
Sure.
Okay, maybe everyone can turn on your camera, and Miss Asma, can you help me to take a picture from everyone?
Sure. So everyone, please smile. 1, 2, 3. Okay, wait a minute. Another slide. Okay. 1, 2, 3. Smile. Okay. And then one slide again. Wait a minute. Okay. So 1, 2, 3, and smile. Okay. Thank you.
Okay.
Professor
Thank you.
Alan.
Thank you very much,
everyone.
Thank you.
I
very
represent
much.
from I got a message from our head of department. He say a lot of thank you for you to giving lecture this day, and we hope we can still joining and continuing this lecture for next Thursday and continue with Professor Carmen for the Friday.
Yeah. Well, everyone have a good weekend, and I look forward to talking to you next week.
Okay.
Thank you.
Good night, Professor Alan.
Thank you, everyone.
Thank you very much. Bye
Thank
bye.
you. Good night. Salam. Terima kasih Bapak Ibu. See you next week.
Terima kasih, mohon izin live.
Sami-sami. Matur nuwun Pak Jadvan. Bapak Ibu dosen serta semuanya. Pak Doni, jangan live dong.
Nanti ngisi absensi aku.
Oh ya, jangan lupa isi absensi Bapak Ibu. Tadi saya share
Bukan
lagi
tiga
karena
sertifikat aku Ibu Rama nanti.
Dihukum nanti Pak, dapat
Nah, ya
sertifikat.
itu, saya
nanti
takut ya. Saya
kalau
isi
nggak
dulu.
isi sertifikat benar nanti saya nggak kasih sertifikatnya.
Dikasih sertifikat tanah Pak nanti Pak kalau ngisi.
Waduh.
Nah itu sih tak harapkan itu Pak Anteni.
Mau juga Pak kalau misalkan dikasih sertifikat tanah. Matur nuwun semuanya. Pak Doni bentar ya, bentar.
Ini nanti ya, kalau yang
apa.
Prof Carmen Bu Yuni aja Pak yang ini yang Maju.
Udah lampu Pak Doni aja loh.